Okay, I would like to discuss a set of results which is known as Borel Canterli Lemmas, which is very, very general and easy to remember. And so it's so general that it is very, very useful. So the first so the Borel-Canterli lemma says that if you have a sequence of events and the sum over n1 infinity of the probability of these events converges, then the probability that an occurs infinitely often is equal to 0. You see, it's very, very general because there is no assumption on what these events are or what are their property, their independence. So as long as the series of their probabilities converges, then at most a finite number of this event will occur almost surely with probability 1. Okay? So also the proof of this statement is very simple. Because essentially the statement that an occurs infinitely often, so if an occurs infinitely often, then for any n positive, no matter how large, it has to occur for small n which is larger than large n. So this event is contained in the event which is the union from n equal to n infinity of the an. Okay? So this is the event that at least one of the events from n onwards occurs. And of course, if it occurs infinitely often, then at least one of these events this should be true. Okay. And okay, so this means that the probability that an occurs infinitely often must be less or equal than the probability of this event of an. But by the subadditivity, this is less or equal to the sum from n equal to n to infinity of an. But now use also the probability of an. But now if the series converges, then it means that when I take n very, very large here, I can make this term as small as possible. So in particular, I can take it to 0 if I take n going to infinity. Okay? I can make this term arbitrarily small. Okay? And so this means that this probability must be equal to 0. Okay. So as you see, it's a very general result. So for example, we can apply it to the returns to the origin of a random walk. Now, you remember we discussed this already. So we take a random walk, which is just the sum from 1 to n of n random variables where these xi are equal to plus 1 with probability p and minus 1 with probability 1 minus p. Okay, so this is our in general biased random walk when p is not equal to 1/2. And then the event an that we are going to consider is the event that s after 2n steps the random walk goes back to the origin. Okay. And as we have seen, the probability of this event is equal to 2n choose n, because we have to make n steps up and n steps down, times p times 1 minus p, p to the n times 1 minus p to the n. And asymptotically, what we have seen is that this can be written as 1 over square root pi n times 4p times 1 minus p to the power n. Okay, this is what we have seen in the previous lectures. So now, if p is different from 1/2, then this object is less than 1, which means that as n goes to infinity, this goes exponentially to 0. And if this probability goes exponentially to 0, then it means that this series converges. And by this, by Borel-Canterli lemma, you can conclude that the probability that a random walk, a biased random walk, will go back to the origin an infinite number of times, infinitely often, is equal to 0. Or that almost surely the random walk will go back to the origin at most a finite number of times. I remark that here almost surely means that does not mean that it is impossible for a random walk to go back to the origin an infinite number of times. You can clearly think of paths that go back to the origin an infinite number of times. But what it means is that this ensemble of all these paths that go back to the origin an infinite number of times has probability 0. Okay? So it is not strictly impossible, but in practice it is. It will occur with 0 probability that random walk goes back to the origin an infinite number of times. So when p is equal 1/2, of course, then this 4p times 1 minus p is equal to 1, which means that the probability of an goes as 1 over square root n, and you cannot conclude anything because then that series diverges. But you can conclude something for a d-dimensional random walk. So now this is just a generalization of a random walk to a vector that has components, each of which is an independent random walk. Okay? So, so this means that you can plot so a trajectory of this random walk. If you plot it on its say coordinates, it will be something like where essentially each component, both the x and the y component will go up and down following a random walk. Okay. Now you can define an event an as the event that S2n is equal to 0. And so for S2n to be equal to 0, it means that all of these independent random walk should go back to the origin. So then the probability of this event goes as n to the minus d over 2, because it's just the product, the probability of this is just the product that each component S2n I is equal to 0. And you see that if d is larger than 2, then the series, this goes faster than n to the minus 1, then this series converge, and you can conclude that a d-dimensional random walk will not go back to the origin, will go back to the origin at most a finite number of times. Okay? And these are quite interesting results. So for d equal 1, we have shown that the random walk is unbiased with p equal 1/2, is recurrent in the sense it goes back to the origin an infinite number of times. For d larger than 2, we have shown that it is transient. D equal 2 is a case which is a bit more difficult, but what one can show is that the random walk is recurrent also in 2 dimensions. Okay, so very good. So one would like also to have a converse of the Borel-Canterli lemma. So, so a converse that eventually tells you that if you have an infinite sequence of events, and this is infinite, then this means that these events will occur infinitely often, almost sure. You know? So this is what we would like to understand, to what extent the converse is true. Okay, so it cannot be true. A simple counterexample that tells you that this cannot be true, because, say, for example, if you take, say, x, which is a uniform random variable in 0, 1, and you take an to be the event that x is between 0 and 1 over n, then you can easily see that the probability of an is equal to 1 over n, and then this series diverges, clearly diverges logarithmically, but this is not true, because the probability that an occurs infinitely often is equal to 0. Why? Because for every value of x, there is a maximal value of n for which these events occur, which is, so if n is larger than 1 over x, then none of the event an will occur. Okay? And so this means that an almost surely will occur a finite number of times. Okay? So indeed, as this counterexample tells you, that this converse is generally not true, is not true, one needs additional assumptions. And for example, if you add the condition of independence, if A1 and a sequence of independent events, then this occurs, then the converse is true, that the probability that AN occurs infinitely often is equal to 1. Okay, so let me give proof of this. Now, let us consider the event, the complement of this event, which is the event that AN occurs at most a finite number of times. Okay, so if AN occurs at most a finite number of times, then there should be a maximal, so from a certain point on, none of the event AN should occur, okay? And so there should exist one value of n, of m, such that none of the events with index larger than m occur, okay? And and the condition that there exists one value of n is means that if I take the union of all m, so at least one of these events should occur, which means that this event is the union for m equal to 1 to infinity of all these events, okay? Now, if this is true, then the probability of this event is 1 minus the probability that AN occurs infinitely often. And this is equal to the probability of this event. By the subadditivity rule, this is the less or equal to the sum from m from 1 to infinity of the probability of these events here, and from m to infinity of AN. Now, but these are all independent events, okay? So if they are all independent events, the probability of the intersection is the product of the probabilities. So this is sum m from 1 to infinity to the product of n from m to infinity of the probability of the complement of the complementary of AN, which is 1 minus the probability of AN. Okay? Now I can use the fact that 1 minus x, for all values of x, 1 minus x is always less or equal to e to the minus x. And write this as the sum, this is less or equal to the sum from m from 1 to infinity of e to the and the product can go to the exponent, e to the minus sum from n equal to m to infinity of the probability of AN. Okay, so now if a series diverges, then any subseries also diverges. So which means that this is also infinite. So if this is infinite, then e to the minus infinite is exactly equal to 0. So this is exactly equal to 0. So if this is equal to 0, then it means that the probability that AN occurs infinitely often must be equal to 1. Okay? Because this is it must be positive. Okay? Okay, very good. So now, see, let me give you an interesting example of how you can think a case where the converse of the Borel-Canterli lemma applies. So imagine that you have a particular text, okay, or say a sequence of letters, okay, x1 to xm, and these xi are just letters of the alphabet, A, B, C, up to Z, and then also the space, okay? And you can put also commas, dots, and whatever, okay? So it's a finite alphabet. Now, let's take, say, a sequence of random variables which is just random and independent, an infinite sequence where these xi also take values as one of these letters, let's say letter say, A with some probability PA, and then you have a probability PB, PC, etc., etc. So you have a certain probability distribution over this alphabet, and you are just generating a random text, okay, as a sequence. Now you have this very, very long sequence of text, and you can take the first m characters from, say, x1 to xm, the second one, etc., etc., or the nth one, say from x n x n minus 1 times m plus 1 to x n m. Okay? Okay, here you have a sequence of m letters, and you can take the event an, which is the event that this sequence is exactly equal to your pre-assigned text m. Okay? Now it is clear that the probability of an is just a constant, because all these letters are chosen at random. Okay? So it is clear that because this is a constant, then this diverges, and these events are clearly independent because each of these letters is drawn independently from this distribution. So we are in the condition of the converse of the Borel-Canterli lemma, and so the probability that an occurs infinitely often is equal to 1. Now, this is true regardless of how long is the text. So, for example, you could take this text as being the Hamlet of Shakespeare, or the Divina Commedia of Dante. And so what this tells you is that if you take an infinite sequence, a random sequence of letters, this contains the Hamlet an infinite number of times. Okay? And by the way, it also contains any other work, any other novel or any other text in probability. So this sequence of random letters contains an infinite number of copies of any book you can be interested in. Okay, so now pair independence is a little bit very strong as a condition. So indeed you can relax it and require only pairwise independence. Okay, pairwise independence, this means that the probability that two events occur, AI and AJ, is equal to the probability of AI times the probability of AJ. Okay? Now, let me give you an idea of how you prove this result, because it's an application of the ideas that we have discussed in previous lectures. It gives you an idea of what is the logic that is used in probability. Okay, so let's consider the random variable Sm, which is equal to the number of events An that occur up to n. Okay? So the expected value of Sm, so in a sense you can write this Sm as a sum from n equal to 1 to m times a variable that you can write as say 1 an, and this variable is equal to 1 if an occurs and is equal to 0 if an does not occur. Okay, this is called an indicator variable of the set an in mathematics. So then it is clear that the expected value of Sm is equal to the sum of n from 1 to m of the probability of An. And why? Because essentially the expected number of events that occur, I mean each event occurs with probability P of An, so if it does not occur with probability 1 minus P of An. So if you want, the expected value of this is just P of An. Okay? Very good. So now you can use Chebyshev inequality for the random variable Z, which is Sm divided by the expected value of Sm minus 1. And what does Chebyshev inequality tell you? That the probability that Sm over the expected value of Sm minus 1 is larger than epsilon. This must be less or equal than the expected value. So the expected value of this random variable here, so divided by epsilon squared. Now the expected value of z squared, you see, so it's essentially given by the variance of Sm divided by the expected value of Sm squared. No, because you can multiply by expected value of Sm, and then when you take the expected value of z squared, then you just get that. And also you can figure out that when you compute the variance of Sm, essentially this is a simple calculation, but if you take this expression here, because of pairwise independence, so here you would have the sum over n and n prime of the expected value of 1 a m n minus expected, well, minus p of a m a n times the same thing for a n prime minus probability of a n prime. Now, when you all the terms with n are different from n prime, because of independence, this expected value factorize, and it essentially gives you 0, because the expected value of this is equal to this, and expected value of this is equal to that. So the only term which remains is the one where n is equal to n prime, and this is just the sum over n of p of the probability of a n times 1 minus the probability of p of a n. Okay, if you it's a simple calculation. Now this is clearly less or equal than the term where you remove this one. So this is less or equal than the expected value of Sm. Okay? So, so this object, if this is less or equal than the expected value of Sn, then this object is less or equal than 1 divided by epsilon squared times expected value of Sn. Okay, so now what we have shown so far is that because the expected value of Sm is equal to this sum here, when n goes to infinity, this diverges. And so what we have shown is that the probability that that Sm divided by this is different from 1, is larger than epsilon, then this probability asymptotically is going to 0. Okay? So what we have shown is that Sm divided by the expected value of Sm converges in probability to 1. So this tells you that the number of events that occur essentially diverges as its expected value, which is essentially the sum up to n of this term, okay, or this thing, okay. And very good. So indeed, say you can prove also that not only that this occurs in probability, but also that it occurs almost surely. And the main idea here is to show that this event here occurs, the probability that this event occurs infinitely often is equal to 0. So one way of doing this is to take a subsequence mk where subsequence is mk such that the expected value of Sm is larger or equal to k squared, for example. Okay. Now, if you take m and k of this form, then you see that the probability of having this deviation is upper bounded 1 over epsilon times k squared, which means that the sum over all k of these probabilities will converge, because it's upper bounded by a series that converge. And then this means that you can apply the first Borel-Canterli lemma and show that the probability that over these subsequences, the probability that you have an infinite number of these deviations from the limit is equal to 1. So almost surely you have a finite number of deviations larger than epsilon. And the last step is to show that this does not only occur for these subsequences, but it occurs for the whole sequence. And but essentially, this is the main say inside of how you use these results to establish the converse of the Borel-Canterli lemma for pairwise independent events. Okay, so okay.